Hi everyone, I'm Ray Burns. I'm the Director of Research and Development for Lucas Oil Products, and today we're in the lab checking out all the latest and greatest equipment we have to qualify and test our amazing products. Right here I have a piece of equipment called a mini traction machine. This is a modern research grade instrument available in tribology and lubrication labs all over the world, and we use it to measure the friction and flow characteristics of fluids that we develop and test here in the lab. Typically, this piece of equipment works by taking a polished steel disc. I have one here. We use a new disc and a steel ball for every test. And this machine mounts these two together and rotates them both against each other independently inside a temperature controlled chamber. And that lets us look at how the products perform across a wide array of different lubricating conditions, whether it be different speeds, different loads and pressures, different temperatures. This machine lets us look at it all at once. So this is a new 52100 steel disc that's used for the MTM test. This is polished down to 0.05 microns RMS roughness, so it's very fine. Anytime you run a frictional test, the roughness of the surface you're testing matters. We'll mount the disc inside. Then we'll use the locking nut to make sure it's attached. Next, we're going to mount the ball. You can see it's also a 52100 polished steel ball, also polished to a 0.05 micron roughness. Today, we're going to test one of our high-performance Lucas motor oils. All right, now that our fluid's loaded, we're going to run this at slow speed just so we can see what the inside looks like. Normally, this is in a temperature-controlled environment, so we want to make sure you guys can see what it looks like. Now you guys have seen what it typically looks like inside, we're going to close it up and get ready to run an actual test. First thing that goes on is the metal lid and the Teflon lid. We'll lock that down, and now we're ready to run a test. We're going to run a simple friction curve for this fluid. We're going to run it at 100 degrees C at 39 newtons of load. That basically means a contact pressure of 1 gigapascal. That's like 1,000 atmospheres. So take what the air you're breathing right now, multiply it by 1,000. That's how hard they're going to be pushed together. That's extreme. That's like the load inside of a main bearing in your crankshaft. Then we're going to run that over a range of speeds from 1 meter per second all the way down to 0.1 meter per second of fluid velocity into the contact. When this test runs, the ball and the disc are actually rotating against each other, and we're trying to maintain a constant ratio of the relative speed of the ball and the disc. That's called the slide to roll ratio. And as we change those, it changes the speed of the fluid going into the contact. Each time we measure the coefficient of friction at a given speed, we actually measure it with the ball rotating in one direction, and then we reverse the rotation and measure it with the ball going in the opposite direction as well. Those two measured coefficients of friction are reflected in the final data we measure to give us the coefficient of friction at that condition. It repeats this test 4 times, so we don't just run things once. We run them over and over and over again to make sure we get reliable and repeatable results. Now we're going to get our disc out and we're going to take a look at the wear scar. So that picture is 5W30 motor oil that we ran on our mini traction machine. And on the computer with the microscope, I've got the wear track pulled up. You can see that the wear track follows the rotational path of the ball. So those vertical stripes on the picture you're seeing actually correspond to wear marks from the ball and the disc being in contact. In this experiment with just regular motor oil, we've measured 93.7 microns of contact patch after we've run this test 4 times in repeat. So this disc and ball were used and 4 repeats of the same experiment were run. That's caused a wear track of 93.7 microns. So we can compare that number to the same experimental conditions with a different fluid to get a relative comparison of their performance. Now we'll switch over and we'll look at a disc from an experiment using the same fluid that's been treated with Lucas Oil Stabilizer. Now there's the edge of the disc. Now we're moving onto the polished surface. So we're looking at the entire polished surface, and there's almost no wear track that we can see. Let's look at them this way, because we're having some difficulty finding the wear scar for the fluid tested and mixed with Lucas Oil Stabilizer. This disc is 5W30 motor oil with nothing else in it, and you can actually see the wear track on it. This disc has the same fluid that's been treated with 20% Lucas Oil Stabilizer, tested in the exact same way on our mini traction machine. This one, with the heavy duty oil stabilizer, there's basically nothing. Can barely faintly see it, and we're having trouble finding it in the microscope. Thank you guys for coming to the lab today and hanging out with me. Hopefully you got a better sense of all the rigorous testing that we put behind the products we develop here at Lucas Oil Products. Appreciate your time, and just remember, the proof is in the product.